There's Christmas break and New Year, which is a major holiday. So this is always quite a resting phase. But now we are resuming, and the plan for today is that I give an introduction into seeded free electron lasers, because that's a very interesting and certainly very prospective new development in the EUV, so extreme ultraviolet free electron laser business, and also in the X-ray laser business. As you will see towards the end of the presentation, there's actually a very recent breakthrough result, which is not yet published, but already available as a preprint, which represents a very interesting new development. You will see this in the end. I will not spoil you now. And we may have some time towards the end of my lecture to look once more into the ZFEL Python simulation that we had started looking at before Christmas break together with Asbjørn. So Asbjørn is really the master of the Python simulations. I don't know if you have had more time to look into these Python simulations, or you're interested in getting this simulation up and running on your computer. If you have not had the chance to do that 2 weeks ago, then today would be another chance to do it. And the reason why we wanted to pick up on this ZFEL simulation today is that the simulation simulates XFEL activity both in the SASE mode. Remember that XFELs until now mostly are operated as SASE lasers, meaning that the lasing process is started from the noise, so from spontaneous emission, and that causes significant fluctuations and like uncertainties in the parameters of both the spectrum and the timing of the pulses. So of course, there's a great desire to control the lasing process more accurately. So have some external control of when exactly the pulse starts lasing, and also what exactly the spectral properties are. And this is actually the topic of today's presentation, which deals with seeded FELs. And so the ZFEL Python simulation both simulates the SASE, the spontaneous lasing, and also the seeded lasing. So it's a nice way to computationally investigate a little bit more and get a better feeling of how these FELs work, and how you can improve their spectral and temporal properties by seeding the FEL. And so now let's have a look at what seeded FELs actually means. Just a brief recap what unseeded, so SASE lasers look like and how they work. Yeah, I mean, SASE means self-amplification of spontaneous emission. So it's the spontaneous, like stochastic, undeterministic light emission which triggers the FEL process. And this is a random process, so there's no way to accurately control what the color, so the spectrum of the pulses is, and also when exactly the lasing starts. So exactly the timing is rather weakly controlled in this SASE mode, so which results in strong fluctuations on a shot-to-shot basis. So every SASE XFEL pulse actually looks very different from the next one. And of course, this is mostly a drawback, because ideally you want exactly the same pulses coming every time and with a high repetition rate. This is not the case for SASE pulses. There can be, you can imagine actually some applications where this random fluctuations of the pulses can actually be exploited to, let's say, explore a wider range of colors, yeah, of spectral components and also timings. But I will not talk too much about this. Just to mention, and if you're interested, you can ask me later. There is actually ways to actually exploit these strong pulse shot-to-shot pulse fluctuations and make this a feature, not just a drawback. Yeah, just as a reminder, these XFELs, well, actually the first XFEL that was a SASE FEL actually running in the X-ray regime is this LCLS laser at Stanford in California. Quite a large scale facility, but it's not the biggest one. Nowadays, the European XFEL in Hamburg is significantly larger than this one and more powerful. And yeah, this is a typical SASE output in terms of the spectrum of the pulses. And what is shown is three just randomly selected X-ray pulses from this train of X-ray pulses generated by LCLS. So this, yeah, they actually every pulse at these big and very expensive free electron laser facilities, every pulse is labeled by its bunch number, typically it's called. And for every pulse arriving with 100 hertz, or nowadays actually even with multiple kilohertz repetition rate, for every of this pulse, the spectrum is saved, and many other experimental parameters are saved, such that you can really reconstruct in your data analysis after the beam time, you can reconstruct what exactly the properties of every single pulse was. So this, you can imagine, needs enormous amounts of storage space for storing all these data, in particular when it's like imaging data. But that's another challenge. So just to mention that these XFEL facilities are not just like large scale and very expensive hardware or like laser and accelerator facilities, but they also involve a whole lot of computing power and data storage and data handling to cope with these enormous amounts of data that are constantly produced during the operation. But okay, back to the SASE spectrum. So you can see like three randomly selected spectra of SASE pulse, and you can see that every spectrum looks very different and is extremely spiky and noisy. But this is exactly the characteristics of this SASE mode, and it's a consequence of this random stochastic emission process that starts the coherent amplification in the undulator out of the noise. And only by averaging over many of these SASE pulses, then we get this red line. The red line is an average of 7,000 of these shots, which looks more like what we would expect for for a laser emission spectrum, like some kind of a smooth Gaussian function. But this is only after averaging over all these many pulses. Every pulse by itself has this shot-to-shot fluctuating spectrum. And that, of course, we would like to remedy and get something like this red spectrum, but really for every shot, for every laser shot, always the same. That would be much better for many experiments. Yes, and so actually just another reminder, the very first SASE free electron laser, maybe you remember, that was actually not operating in the X-ray regime, but it was this flash laser, the free electron laser in Hamburg, which was actually a development or like a change of purpose of a linear accelerator facility that originally was designed for collision experiments in particle physics, but This has since 25 years now been, of course, rebuilt and optimized to be a full-fledged free electron laser photon source. So, of course, no more particle collisions and no more high energy physics. This is the whole facility in Hamburg now is entirely devoted to photon science. And basically, the only remaining parts from the accelerator or particle physics times are these linear accelerators. And it's actually a two-stage accelerator structure with yeah, a short and a long accelerator. With magnetic, what is called magnetic chicanes. So these are just magnetic or dipole magnet structures. We will come to that a little bit later. These are dispersive sections to introduce controlled dispersion into the electron optics or into the electron propagation of the electron bunches. And then nowadays, the Flash facility has actually two free electron lasers. One is the original Flash 1, and the other one is Flash 2. And the main difference is that Flash 2 is what is called a variable gap undulator, where the gap between these arrays of permanent magnets can be varied, just like in most synchrotrons, or actually every synchrotrons, and also in all the modern free electron lasers. And this variable gap, by varying the gap, we can control the magnetic field, and by the magnetic field, we can control the spectrum, the gain spectrum of the undulator. Whereas in Flash 1, this is fixed gap, so there's very little control of the wavelength or the color of the laser pulses that can be used here. And then we have these experimental halls at the end where the experiments are. And these are now, this is again one selected SASA pulse represented as yes, the variation of the wavelength normalized to the central wavelength lambda, just to have it symmetric around 0. But you can see that it's an extremely spiky spectrum in the spectral range. And since the spectral range and the temporal, so the time profile, are usually related by Fourier transformation, also in the time domain, you can see that by far this is not just one single femtosecond pulse, but it's actually a whole quite random structure of pulses. And if now you imagine that we want to do some very controlled pump probe experiment by shining in a first pump pulse and then probing with a second probe pulse, then if the probe pulse looks like this, the timing is quite weakly defined, right? This is definitely not ideal for getting high time resolution in a pump probe. So this we want to improve. And just as a general consideration, if we assume now that in principle the gain spectrum or the spectral range, so the photon energy range, coming back to LCLS, which is this X-ray laser. So here we really have X-rays in range of 6 kilo electron volts. Now, averaging over all these pulses, we get this red spectrum, and assuming this is essentially the range of photon energies where we can get amplification, right? This is the gain spectrum of the undulator. So in principle, if we did everything right and we would exploit all these different frequencies that can be amplified, the question is, I mean, how short could the pulses possibly be if we would manage to get what is called Fourier transform limited pulses? Yeah, the transform limited pulses means that the pulse duration would be just given by the spectral width of the spectral distribution in the pulses. And for these Fourier limited pulses, which are quite easy to achieve in the, let's say, visible or infrared range with femtosecond pulses, for these Fourier limited pulses, we have the general time bandwidth product that limits the duration of the pulses, because according to Heisenberg's uncertainty principle, in the end, the product of time uncertainty and energy uncertainty, or energy and frequency, are just proportional. So that so this product of time uncertainty and frequency uncertainty is a constant. And if we assume a Gaussian shape of the spectrum, and therefore also a Gaussian shape of the pulse shape in time, then the time bandwidth product exactly equals this 0.44. That comes from just Fourier transformation. But we have this constant here. If you want to learn more about Fourier limited pulses and ultra short pulses, then I can recommend this excellent course here taught by Shiva Ramakrishnan at IIT Madras. I'm sure that this is being discussed in detail in this course. But now we just use this formula for the time bandwidth product to estimate what would be the shortest possible pulses, assuming this kind of bandwidth for the amplification of the X-ray pulses. So what is the Fourier transform limit for such a spectrum of X-ray pulses? This is now a little exercise for you. Please pull out your pocket calculator or use your computer and see what you get. So the question is, what is delta t? The delta t, this we take as the pulse duration, the minimum pulse duration, given this spectrum of the X-ray pulses. Please, the first of you who has a result to offer, shout it out. It's just a little calculation to do. So essentially isolate for delta t, right? Delta t is the time duration. And remember, photon energy in electron volts. So how do you convert electron volts into frequency? Well, 1 electron volt, take it times the elementary charge. That gives you the energy in joule, and that is equal to an energy h times nu. So you have to take into account the elementary charge, 1.6 times 10 to the minus 19. What is it? Coulomb. And you have to remember h, the Planck's constant. Any suggestions? If you're too lazy to plug in the numbers, but you feel confident enough to give a good estimate, then please just give an estimate. How short would the pulses be, or given that this is the pulse spectrum and the pulses are Fourier limited?
Is it 10 raised to minus 11 seconds?
10 to the minus 11 seconds. So that would be 10 picoseconds, right? A picosecond is 10 to the minus 12.
Yeah.
10 picosecond. I mean, it's probably a guess, but it's way off.
Is it like 10 power 16?
Yeah, that sounds
Around.
much better.
Yeah.
Yeah, okay, this is the calculation. Just take this 0.44 divide by so I mean, let's take here I just took a bandwidth of 20 electron volts. I mean, assuming that the full width half max of this Gaussian red curve goes from 5,990 to 6,010. This is 20 eV. So I take delta nu as 20 eV. Okay, convert EV into energy in joule. So we have to take times the elementary charge and then divide by H to get it into frequencies. And that gives me 0.09 femtoseconds. So yes, this is roughly 0.1 femtosecond is roughly 10 to the minus 16 seconds. That was correct.
Yeah, I took the central frequency.
So you took 6 kilo electron volts.
Yeah, that's why it was like 4 orders.
But then you should have gotten a much smaller value, in fact, right? Because we divide by the frequency. So
Yeah,
if instead of taking 20 eV, if you took 6,000, you should have gotten something even smaller.
yeah, correct.
But anyway, I mean, the point is that if we were able to like get Fourier limited, nicely controlled pulses, just like in usual femtosecond lasers, then it should be possible to actually not even have femtosecond pulse, but attosecond pulses. Yeah, this is 90 attoseconds. So just to tell that in principle, with the available XFEL technology, like with such a gain curve, if we could manage to get rid of these random fluctuations, then we should already naturally get attosecond pulses, which is of course would be very interesting and very promising for many high experiments where you really need extremely high time resolution. I mean, there's a whole research field that is just trying to push the limit of the pulse durations to ever shorter pulses, and in particular into the attosecond pulse regime. And soon we will hear more about attosecond pulses by you guys presenting two experimental approaches to reach controlled attosecond pulses with XFELs. But yeah, so this is the good news that in principle we should reach attosecond pulses, or it should be possible if we could control the lasing process better than just getting it started out of noise. So how could we do this? I mean, of course, the ideal case would be to build a laser just like we are used to having lasers, yeah, with an optical cavity around the gain medium and have like these high reflective mirrors to get the light bouncing back and forth between the mirrors many times and like very strongly coupling to the gain medium. Then this is what a usual laser looks like. And if you remember the introduction into the FEL topic, it is actually possible to build free electron lasers in this way. Only it's not possible to build lasers in the X-ray regime, because in the X-ray regime, usually there are no mirrors to build a cavity around the undulator that acts as a gain medium. It only works in the infrared and in the terahertz range. Yeah, I mean, remember these undulators in principle can amplify any wavelength, going from very long wavelengths, so infrared over UV up to X-rays. So, and there are infrared and X and terahertz free electron lasers that are being running at different facilities. I presented two in Europe, and those are actually built exactly in this way. So there's an optical cavity that provides the feedback of the light And in this case, we have a nicely well-controlled laser activity with a like very sharp spectral line and all that. But yeah, in the X-ray regime, it's almost impossible to build a resonator because there is just no mirrors available because X-rays, particular hard X-rays, I mean, they just go through any matter. There's no reflective surfaces. So this is not the option. You would think this is not the option for X-ray FELs. So how about then at least instead of having the lasing start just out of the noise, at least we could possibly inject a well-controlled laser pulse from outside, an external pulse injected into the gain medium, into the undulator, and then start the XFEL lasing process, not out of the noise, but uh, by imprinting the spectral and temporal properties of this external pulse. But for that, of course, then you would need an X-ray laser pulse to start with. Yeah, you would have to have some kind of femtosecond laser that already lasers in the X-ray to actually start this FEL X-ray lasering process. And again, there is no other way to produce X-ray laser pulses than using a free electron laser. I mean, nowadays there is these high harmonic sources that just about reach the X-ray range. So there is actually also some activities going on trying to do exactly this, like to seed. This process, by the way, it's called seeding. So we would seed the lasing process in the undulator by an external well-controlled laser pulse. And yeah, there is activities of trying to do this with an HHG, high harmonic pulse. But so far as I know, this has not been very successful. And the main reason is that these high harmonic pulses are just so weak that they are not efficient in actually seeding the FEL activity because they are with a high harmonic generation. Typically, we're talking about nanojoule or even sub-nanojoule pulse energy, so very, very weak pulses that are just not strong enough to start the FEL process. So how else could we do it? Does anybody of you have a suggestion? How could we seed the X-ray FEL process by an external well-controlled pulse to avoid these like the lasing starting out of the noise, which produces all these fluctuations? How could we generate a controlled X-ray pulse to seed the lasing process? This is a question to you, to your creativity as becoming experts in lasing and FELs. Jayesh, Asbjørn, Thanuv, any suggestions? How could you produce a better controlled X-ray pulse that will then be amplified in the undulator instead of just letting the undulator start lasing by itself in this like stochastic way? Any suggestions?
Could you put another undulator in front and then hope that you can use a free electron laser as the seed?
That's a very good idea, but then the question is, why should this other undulator have a better controlled spectrum or better controlled pulse timing than this undulator?
Well, you would.
But I mean, you're completely right. This is actually the way to go. But somehow you would have to even if the first undulator that's supposed to provide the seed, even that, if that is also, I mean, this is then obviously a Sase undulator, right? Because again, it doesn't have any seed. But then you could possibly try to improve these pulses produced by the first undulator before injecting these pulses into the second undulator, right? So how could you improve the properties of the first undulator pulses?
They would be improved by passing through a monochromator, right?
Yes, exactly. So that's what is called self-seeding. And self-seeding was first demonstrated using the first extreme ultraviolet Sase, FEL, so the flash laser in Hamburg. And it was first demonstrated in the extreme ultraviolet, so not X-ray, but slightly longer wavelength. And the reason is that here implementing exactly the scheme that Asbjørn suggested is very straightforward. Yeah, you have this first undulator that lasers in the Sase mode, so this produces these randomly fluctuating pulses, but then these pulses are passed through a monochromator, so basically they're diffracted from a diffraction grating, which picks by the Bragg condition, it picks exactly one specific wavelength. So this basically cleans up the spectrum, and this cleaned up spectrum is then injected into the second undulator as a seed to seed the amplification and the lasing in the second undulator. And the result you can see on the top, this is the Sase spectrum, essentially what the first FEL produces, and the corresponding time trace. So the pulse shape, very spiky. And on the bottom, you see this cleaned up spectrum after passing the pulses through the monochromator. So of course, there only one sharp wavelength is like survives or is filtered out by the Bragg condition, and only this wavelength then is actually amplified in the second undulator. So we get this one single sharp, nice line. And at that time in the beginning, I mean, from this one sharp line in frequency or in the wavelength range, you would actually expect a longer but very smooth time profile just by Fourier transformation, right? It didn't exactly look so nice and smooth. It still has this spiky structure, but this was the beginning of self-seeding and self-seeded lasing. Nowadays, actually, the timing structure looks much better. So we actually get nearly Fourier transform limited pulses, so meaning like a nice and smooth time structure of the pulses as well. But yeah, so this is the basic principle of self-seeding. Just produce Sase pulses to start with, filter them spectrally, and then amplify them further. Now, this scheme in the X-ray regime works slightly different, because if you remember, for X-rays it's much harder to realize a grating to diffract the light, right? Because I mean the spacing between the grooves has to be on the order of the wavelength. And as long as we are talking about like 10 nanometers or 100 nanometers, then we can use like artificially fabricated gratings, because with using nanotechnology, we can fabricate like 10 or 100 nanometer groove spacings. But if we are talking now about X-ray, which corresponds to angstrom wavelength, then we need angstrom lattice constants for the grating, and so this is single crystals. So in the X-ray regime, the self-seeding scheme usually is implemented in this way. So we have a first Sase undulator, which produces Sase pulses, yeah, ugly, spiky spectrum. Then we have a magnetic chicane. So I didn't talk about that, but the magnetic chicane, that's essentially just a set of these 4 bending magnets. which are used to just deflect the electron bunches around the corner, basically to bypass this monochromator or the grating. In this case, for X-rays, as I said, it has to be grating with angstrom lattice constant. So this is just a single crystal diffraction device. So it's basically a thin single crystal, usually diamond, a thin diamond plate, which is used for like monochromatizing the pulses. Of course, the light just goes through straight and then is superimposed with the electron bunch that moves around the corner, and then with a proper delay between the X-ray pulses and the electron bunches, then the two are superimposed inside the second undulator, and then the actual like cleaned up X-ray pulses are being amplified in the end. And I mean, the way here it's implemented is that this is just a detail, but it's an interesting fact actually that this Bragg or the crystal that induces diffraction is mounted right into the X-ray beam, meaning that the Bragg condition, like the constructive interference and diffraction, diffracts a small portion of this broad spectrum out of the beam, whereas the portion that is transmitted into the second undulator is the whole remaining SASA spectrum minus this very narrow frequency range, which just fulfills the Bragg diffraction condition. So yeah, if you look closely, so the spectrum that is actually being amplified, or not amplified, by the spectrum that's transmitted going on into the second undulator is this SARS spectrum minus there's a small dip at this specific frequency where the Bragg condition is fulfilled and where the light is diffracted out of the beam. So it's essentially it works as what is called a notch filter. So it cuts out this very narrow line out of the spectrum. And the point is that by that it actually doesn't matter so much whether we filter out like here a positive sharp line in the monochromator that we just looked at before, or whether we filter out a negative sharp line. In either case, this produces in the time domain a longer what is called a this is a diamond, a longer what is called a wake pulse, or much more monochromatic, because it's a sharp notch in this case, a monochromatic tail. And here the timing is chosen such that this delayed and much longer monochromatic wake pulse that corresponds to this narrow dip in the spectrum, this is the one that is superimposed with the electron bunch that travels around the magnetic chicane, and that's the part that is then being amplified in the second undulator. So the resulting narrow spectrum that we get after the second undulator as a positive strong component in the spectrum actually is just where the dip in the spectrum was in the first place after passing through this diamond single crystal transmission monochromator. You have to think about it for a while, like how can a dip result in a positive peak? But this is all the mystery of Fourier transformation between the spectral and the temporal range. Anyway, so that's the way it's being done in for X-rays, and the result is the same. So out of this broad and spiky SASA spectrum, in the end, we get a nice and narrow, sharp spectrum after the second amplifier, the second undulator. Okay, there's actually another way to do this seeded lasing. So far we have talked about self-seeding because it's essentially the whole FEL which itself is used for seeding the lasing process. What would be even better is to have actually an external, very well-controlled laser pulse to seed the lasing process. And but there the problem was we don't have this X-ray laser pulse to start with because we need an X-ray laser. And for in the X-ray lasing, in the X-ray domain, it is true. So for the seeding process for X-rays only works in the self-seeding scheme, but in the EUV range or the extreme ultraviolet, there is a way to actually use an external, well-controlled femtosecond laser to do this seeding process. Of course, it's very hard to produce an intense XUV, extreme ultraviolet laser pulse in the first place, but there is a trick, and this trick is called high gain, high harmonic generation. And the trick is that, again, we use two undulators, two successive undulators with a magnetic chicane that acts as a dispersive section in between. And the trick is now that the first undulator, which is called the modulator, is tuned exactly in resonance with the seed, which is typically in the UV, because it's still quite easy to produce femtosecond laser pulses in the UV range, for example, by third harmonic generation, THG. This stands for third harmonic generation of a titanium sapphire laser. I mean, those of you who have some experience with femtosecond lasers, you probably know that the TiSAF 800 nanometer pulses can quite easily be doubled to get 400 nanometer, or also tripled. So third harmonic generation is still quite easy to implement using crystals to get 366, or even using the OPA stands for optical parametric amplification. This is another nonlinear technique. We can quite easily get down to about 200 nanometer UV pulses. And 200 nanometer, here we can actually tune the undulator, or this first undulator, which is called the modulator, we can tune it into resonance. Remember what undulator resonance means. It means that the like electromagnetic undulator radiation emitted by the undulator, this is given by this formula, where lambda U stands for the undulator length. So that's just these like roughly 2 centimeter length between the permanent magnets, and gamma is the relativistic Lorentz factor. So this wavelength at which the undulator would like to emit light, if that exactly matches the wavelength of the seed laser pulse, let's say 200 nanometers, then we get efficient coupling of the seed laser with the electron bunches in the undulator, and eventually we would get FEL, so amplification and FEL activity exactly on the wavelength of the seed. I mean, in this HGHG scheme, the first modulator is actually a quite short and low gain undulator, and it's actually only used for inducing micro bunching for basically imprinting an energy modulation onto the electron bunch at exactly the wavelength of the seed. Then we have a dispersive section given by magnetic chicane, and that the trick is in this magnetic chicane, an energy modulation induced by the seed laser is converted into a density modulation. So basically in real micro bunches, which then start emitting coherent radiation in the second, much longer undulator, which is also called the radiator. Yeah, it starts emitting coherent pulses or coherent radiation right from the start. So there's no, then in this actual radiator, the main undulator, we don't have to wait for spontaneous emission to start the SARSE process. Here then we have the micro bunching, so this readily shaped micro bunched electron bunches already starting from the start to emit the coherent radiation. So just to show you how this looks in the phase space. So we have energy versus phase. So this is like the electron bunch as it enters the modulator. Then when the electron bunches resonantly interact with the seed, yeah, we have this resonance condition fulfilled that the emission wavelength of the modulator just matches the wavelength of the seed. Then we have resonant coupling, and we get an energy modulation in the electron bunch. Then when the electron bunches pass through this dispersive section, we get we introduce dispersion, meaning that the faster electrons move at a have a shorter flight path through the magnetic chicane and a shorter travel, and the slower electrons have a longer travel. So this induces this shifting in the phase space. So they acquire this this phase relation, which is no longer just sinusoidal. That's an important point, because what we need is that, like in the end, we want in the radiator, in the second undulator, we want emission at actually a higher harmonic than the seed laser that we start the seed process, right? I mean, here to start with, like with the seed, we have a UV laser pulse. In the best case, we have something like 200 nanometers, but in the end, we want the FEL lasing at much shorter wavelengths. We want this in the EUV or possibly even in the X-ray range. So the trick is that we induce modulation at the fundamental of the seed, let's say 200 nanometers, but then by passing the electron bunches through this dispersive section, the electron bunches in phase space acquire this nonlinear distortion, which means that we get higher harmonics in the end in the density distribution of the electron bunches as they enter the radiator. And then it's exactly these higher harmonics, which are, or one specific higher harmonic where the radiator is tuned to, and then it's this higher harmonic, which can be up to like the 14th or 15th higher harmonic, which is actually being amplified. Yeah, so the XUV emission in the radiator then takes place at one selected higher harmonic of the seed. So this is how HGHG, high gain, high harmonic generation, works. And I mean, so far there is only one facility where this is routinely being implemented and like works on a routine basis. That's the free electron laser Fermi in Trieste in Italy. And the Fermi free electron laser, that's this linear structure here. So this is a view from above, where you can see that there's this linear building which houses a linear accelerator, undulator hall, and then experimental hall. You can also see this round building. This is the Electra synchrotron facility, which houses the main storage ring and all the beam lines for synchrotron. Yeah, this is a typical arrangement that we always find, that the XFELs are built just next to synchrotron facilities because the technology is largely the same, right? It always has to do with electron accelerators, undulators, and also the beamlines are very similar. And so the Fermi FEL was actually the first seeded FEL, and it's still, I think, the only seeded FEL that works on a routine basis. And the tuning range is, so it's not X-ray, it's extreme ultraviolet, so going from 20 eV up to 300. So okay, 300 is already soft X-ray, but it's only soft X-ray. So this unfortunately does not work in the hard X-ray. They're only self-seeding is the only way. But in this range, we really get through the seeding process very nice, very high spectral resolution in the range of delta nu. So now the width of the spectral line is thousandths or so of the center frequency, much better than in the SARSA conditions. Okay, here it says 100 femtoseconds. Actually, they routinely reach now, I think, 20, 30 femtoseconds, and even attosecond pulse schemes have been implemented. Yeah, typical 10, 20, 30 microjoule pulse energies and quite high intensities. Yeah, you can actually see, so here on the top left, you can see really like live shots of from a spectrometer that measures the spectrum of the pulses or the wavelength distribution on the horizontal. So SARSA, you see all these stripes which correspond to these spikes in the spectrum, whereas in the HGHG mode, like the seeded FEL lasing, very nice and sharp single component. And plus, since you can quite easily control the wavelength of a regular titanium sapphire femtosecond laser, at least if you use an OPA, an optical parametric amplifier, you can tune the wavelength. You can also nicely tune the line of the FEL, because in this HGHG scheme, the FEL properties, so the pulse properties are exactly the ones given by the seed pulse. So if you tune around the seed pulse wavelength, then the free electron laser pulses will just follow, just at a higher harmonic of the seed. And yeah, just to mention that nowadays actually this can be okay. No, wait, this is just another illustration. Okay, sorry, this is another illustration showing, for the example of a seed laser wavelength of 260 nanometer. The external seed is injected into the undulator, the first undulator that acts as a modulator. Then this induces energy modulations in the electron bunches going through this dispersive section. The energy modulations are converted into density modulations, meaning these micro bunches are being formed. But the point is, this micro bunch structure is not just sinusoidal, but it is quite peaked, meaning that it contains higher harmonics in the spatial distribution. And it's actually these higher harmonics which are then being amplified. Yeah, so we get the output at lambda over n, where n is some integer going typically between like 2 or 3 up to 15 roughly. Yeah, and that, of course, in this way we get much better control of the pulse duration, of the wavelength and bandwidth. These are really temporal and transverse coherent pulses, close to transform limited pulses. So much shorter pulses, better controlled spectrum. And yeah, actually even there's a technical advantage that the total length of the main undulator can be shorter, because basically you don't have to wait for the electron bunch to like travel long enough until finally spontaneous emission gets amplified and we get this runaway SARSA process. But since the microbunches are preformed as they enter the undulator, then the FEL activity, so that the amplification starts right from the beginning. So the amplification is more efficient, and we are actually fine with even a shorter undulator to reach like full saturation and get the full amplification of the pulses. Yeah, just as an example how powerful this HGHG seeded lasing scheme is, there is an experiment that was carried out last year, actually. Oh no, nowadays it's 2 years ago. We are in 2026 now, where so I was also part of that team. It's a large team where the seed pulses were not just plain femtosecond pulses coming out of the TISEF laser, but we passed the pulses through a pulse shaper, which induced a specific chirp in the seed laser pulses. And those of you who are not so familiar with femtosecond pulses, a chirp pulse means that the frequency inside in the pulse changes from the leading edge to the trailing edge. In this case, this is an up chirp pulse, meaning that it starts with red components, so a longer wavelength, and then going across the pulse, the wavelength gets shorter and shorter, and in the falling edge, we have the blue components, so the faster, the higher frequency components. So this is an up chirp pulse, it would be called, but you can, of course, in principle, produce any type of chirp if you have the proper pulse shaper for that. And then we injected these chirped seed laser pulses into the Fermi FEL in order to produce chirped XUV, extreme ultraviolet FEL pulses, and like to see how much control do we really have over the pulse properties in this HGHG process. And to test how well this chirping of, well, how well the chirp of the seed pulse actually translates into a chirped XUV pulse, we then performed an experiment where these chirped XUV pulses were focused onto helium atoms as a very simple test systems, where the helium atoms, they were then photoionized, and we measured the electron spectrum of the emitted photoelectrons from helium. And yeah, without going too much into the details, the point was that these are actually intense XUV pulses, and what happens when you send an intense pulse onto, let's say, a two-level scheme. So in these helium atoms, the ground state and the excited state can be seen as just a two-level system. And when you send intense pulses onto a two-level system, you start driving what's called Rabi oscillations in time. And Rabi oscillations in time translate into what is called an Outler-Towns splitting of the levels. Yeah, so you can see that that's the schematic representation, that over time, as the pulse gets intense at the center, then the energy level gets split up into this Outler-Towns doublet. And the point of doing this experiment with chirp pulses is that you can actually control the population in the excitation process through the chirp. If you have a chirp, this is now a down chirp, you would populate more the lower Outler-Towns split state, and with an up chirp, you would populate more the upper state of this Outler-Towns doublet, according to theory. So this we set out to test in the experiment, and the experimental electron spectrum is shown here as a function of the intensity on the vertical axis. So what you can mainly see is that when we cranked up the intensity of the pulses, then actually we could see that this electron peak, which was just a single peak at low intensities, actually splits up into this Outler-Towns doublet, but it's more complicated. There's also some structure in the middle. But the point is that then by changing the chirp, and the chirp is typically quantified by the GDD, that's the group delay dispersion, which has this funny unit of femtosecond square. I mean, those of you who know femtosecond pulses are probably familiar with group delay dispersion, because this is also always a very important parameter that you need to control, like dispersion measurement, dispersion management is an important topic in femtosecond, in the femtosecond laser business. So here we could change the GDD in a controlled way, meaning basically we induce both up chirp and down chirps. And we could see that, yes, indeed, it is possible to control the degree of populating the different Outler-Towns states. Yeah, so for one chirp, the right peak was stronger, so there was more population here in this right state, and for an up chirp, the other state was higher populated. And just to basically show that we have this very fine control of the pulse properties in this HGHG scheme, up to like exactly controlling the chirp in the extreme ultraviolet range. Yeah, another interesting development is that this HGHG process can actually be what is called cascaded. So you can just add another radiator. So you have like the modulator, which creates the controlled microbunches together with the magnetic chicane. You have a first radiator, which that actually produces FEL pulses. And then why not do this in 2 steps? So produce FEL pulses by radiator 1 and use these pulses as a seed for another radiator. Yeah, and have a cascaded HGHG process. And so the benefit is that the jump from the seed, let's say 216 nanometer OPA radiation here, that's the external pulse that we inject. We convert it into 21.6 nanometer, so going to the 10th harmonic, which is already quite a step. But by adding this second stage, we can, again, I think this is the 4th harmonic of the 10th harmonic. Then we can go up down to 5.4 nanometer. So this is already soft X-ray in 2 steps, which is more efficient than if we would try to do this in 1 step, going from 216 to 5.4. This would be going to the 40th harmonic in 1 step. Would be very inefficient. It's much more efficient to go in this 2-step process. And in this way, yeah, so here this is then the spectrum measured after the second radiator, 5.41 nanometer radiation. This is actually reaching the carbon K edge, so the S shell photoionization of carbon atoms, which is a very interesting regime for chemical analysis and like for X-ray experiments. Okay, maybe this is actually enough for today in terms of it's 3 o'clock already. I would say we stop here for today. I think you have heard a lot about seeded FEL activity. I have a few more slides, but we can look at those tomorrow. And then I suggest that now we take a few minutes break, maybe stop the recording, take a few minutes break, and get prepared for the ZFEL simulation. Then in the remaining 30 minutes, we can have a look again at the ZFEL simulation and see again, now that we understand